Okay, so here is where our last video left off. We were looking at the hydrogen atom and what happens as the electron changes energy levels from an outer energy level like 6 to an inner energy level like 1 or 2 or 3. And where we were at is we were talking about if it drops from a higher energy level to level 1, that the energy that is emitted is in the form of UV light. If it is dropping to the second energy tier, N equals 2, that is visible light. And if it is dropping to the third energy tier, that is infrared light. So, when we start looking at hydrogen, there are several equations that we are going to be using. And yes, you can have a 3-inch by 5-inch index card for this. So this first equation up here at the top was an equation that was discovered by Rydberg. He found that the wavelengths for visible light that hydrogen emitted could be derived using whole number integers for n. That is our energy level. So that was the first one who discovered that n is going to be a discrete value. It only worked for certain numbers, 3, 4, 5, 6, and it only worked for visible light, which means an electron dropping to energy level 2. So, borrowing on Rydberg's research, because scientists do share research, was very common at this time. They would write letters back and forth to each other. So, borrowing on Rydberg's research, Bohr discovered and derived, really, two equations. The first one here is the energy of an electron at any energy level in hydrogen. So we have E equals RH, that's Rydberg's constant, it's 2.180 times 10 to the negative 18th joules, times 1 over n squared. That n is an integer, that's counting number 1, 2, 3, 4, 5, 6. So that is our energy level. Now, the second equation that he derived, really this is kind of a 2-in-1, if you will. So this energy of light emitted, there's two equations here on the same line. We have Planck's constant times nu, or a Greek letter meaning frequency in this case. The second equation is Rydberg's constant times 1 over our final energy state squared minus 1 over our initial energy state squared. Now this second form, this Rydberg's constant times the 1 over n final squared minus 1 over n initial squared, that one we use frequently whenever we're looking at an electron that is dropping from one energy state to another. It is not just going to level 2. It could be going to any level. Now, the reason that these are written as equal is because oftentimes we will take this Planck's constant times nu, the frequency, and we will then use that to solve for the frequency and therefore chain that into solving for a wavelength. So let's look at an example here. We have a medical device that's designed to kill infection. It is going to excite electrons to n equals 8, so the 8th energy level, and it's going to cause them to fall to n equals 1. We want to calculate the wavelength that is of the light that is emitted by this device. And then we're going to say, okay, well, what kind of energy is this? Well, we're falling to n equals 1, so we can go back a couple slides and we can say, okay, if we're falling to n equals 1, what kind of light are we looking at? Okay, so it's not visible light that we're looking at. We're falling to the n equals 1 tier. So here we go. We have got our formulas here. We can sub in our levels. We're falling to the first state. We started at the 8th. I'm going to plug in Rydberg's constant. I'm going to solve, and I have my energy is 2.146 times 10 to the negative 18th joules. That's how much energy is released in that electron jumping from the 8th tier to the first tier. And then I'm going to say, okay, well, that's going to equal Planck's constant times the frequency. So I can use that to solve for the frequency. That's the nu here, the Greek letter nu. So Planck's constant is 6.624 times 10 to the negative 34th joules seconds. Yeah, we do have it per wave here because that second is going to be connected to a frequency, which is hertz or cycles per second or waves per second in this case. So we solve for nu. We're going to get that nu in waves per second. We're going to divide over by Planck's constant. That takes us to the final equation, kind of the linchpin, if you will, here, which is that the speed of light in a vacuum is equal to the frequency times the wavelength. Always, cardinal rule. The speed of light is 3.00 times 10 to the 8th meters per second. So we take that, that's equal to our frequency times our wavelength. We divide by our frequency, and we get that our wavelength is 9.26 times 10 to the negative 8th, and that is going to be in meters. So it's meters per wave. That's how long the wavelength is, peak to peak or trough to trough. If I convert that into nanometers, that's 92.6 nanometers. This is UV light. This is UV light. This is not going to be visible to the naked eye. So if we look at different elements, we are going to see different colors of visible light given off. That's because they have unique numbers of electrons, and those electrons can jump to different places. They can jump up, they can fall back down, and so they're going to give off different energies. So there are two basic types of light spectra. There is what we call continuous light spectra. That's where all lines of color are continuously emitted. We also call this as white light. So that would be like taking light from the sun and shining it through a prism, and we can create a rainbow effect. The other that we have is what line spectra, where we only see certain colors of lines. For example, neon signs, we excite them, we get them glowing. We look at them through a prism. As a result, we see discrete values. Only certain lines would be seen. So this is an example of some Bohr model atoms, and we are going to get more into modeling very shortly. Once we finish the history, we're going to be doing a lot of modeling of atoms and the different styles of modeling. So here, when we look at electrons in the energy levels, the maximum number of electrons in any energy level is 2 times n squared. So if we are looking at the first level, n equals 1, it can hold 2. Cannot hold more than 2 electrons. That it's full, it's done. If we look at that second energy level, just a little bit further out, it can hold 8. If we look at the third, it can hold 18. Again, it's further out. The electrons have a little bit more distance. Remember, like charges repel. So they need a little bit more space between them because they're going to be repulsing from each other. So they need their own personal space. Then we have the fourth tier, can hold 32. So if we look at a Bohr model, it looks something like this. The number of protons and the number of neutrons would go in the middle. And then you would have how many electrons you have out on each tier. N equals 1, 2, 3, 4. So this is kind of what that would look like. This is how many electrons are in the energy levels. So when we come back, we're going to look at some more history, some more modeling, and we're going to be building more of these atoms.